Hi everyone. So this is Math 20-1 about absolute value functions and reciprocal function lesson 5 part 2. In part 1 we talk about the reciprocal functions for linear function, and today we'll look at the reciprocal function for quadratic function. So this lesson 5 is split into 3 different lessons, and this will be part 2. Now let me show you this software, this one. All right, do you remember this one? This is a software that you use to do the circle geometry. But here, it can also show functions. So let me show you. The pink line is this function. The pink one is this function here. Do you recognize this form? Or any function in this form, what kind of function are we dealing with? You're right. It's dealing with linear function. Y is equal to mx plus b, looking over here. And then the m can be adjusted on this slider. Like here is something that you can slide to adjust m. Well, what does m do? So as you move this line, the value of m will change. So right now I set it as 0.099 is equal to be 1. It's just the software don't let me make it 1. And then the b value right now is 0.05. It's close enough to 0. Okay, 0. Let's make it 0. So here we go. So let's make the slope 1. Okay, 1. So we have a basic graph y equal to 1x plus 0, which means y equal to x is this diagonal line. And then in this lesson, we learn about another function called g of x, another function which is the reciprocal of f of x, 1 over f of x. And then the resulting graph will be the blue graph. This straight line becomes this blue curve. All right, so we are learning how to connect the two things. They look so different, but they are related. All right, we learned yesterday there are 3 things you can make the connection between this purple line and then this blue line. Okay, how to connect the two things? Number 1, whenever the pink hit 0, what does that become? It becomes an asymptote. Do you see what happened with the blue line? The blue line looks like it's trying to stay away from this invisible line at the y-axis at 0. It can't touch 0. All right. Secondly, there's another invisible line across here, which is the x-axis. See, look at the blue line. It's trying to approach it, but didn't cross. Next is the invariant point. Do you see the pink and blue? They cross at 2 points. Where do they cross? Look at where they cross. They cross at 1 and they cross at -1. Because 1 and -1, when you take the reciprocal, is still 1 and -1, so they don't change, which is called invariant. They didn't change, invariant point. Finally, all the straight line portion will become a curve. Now with this software, you notice if I move the B around, okay, like as I move the B, I cover a lot of linear function. Like the line goes on forever. It just somehow didn't keep going. But then you see its corresponding reciprocal function are very similar, right? If I move my function to here, see, the vertical asymptote is still, well, it's here where the 0 is. And then the x-axis is still the horizontal asymptote. And then where do they cross? They cross at 1 and -1. Hey, you say no, Mr. Chang. It crosses at 2 and 4. They cross at 2 and 4, those are the x value. But when I say when the function is equal to 1, we talk about the y value. See, no matter where I move it, where they cross is always at the height of 1. Did you see that? When the y value is 1. You can also change the slope. See? No matter you make the slope very steep or you make the slope very flat, they all cross at 1. Do you see they cross at 1? It crossed at 1. It crossed at -1. It didn't change. And then where they cross 0 is the asymptote. So now reciprocal function is not such a mystery anymore. Now you can see they are related. Given any linear graph, you can write its reciprocal graph. This is the first case. How about the second case? The second case is when the lines are negative slope. It go like this. Well, do you see what happened? Okay, it go like this. Same idea. 0 become asymptote. 1 and -1 are the invariant point, and then you draw the curve around it. Are we okay? So this software show you all the cases. for linear. This way or this way, this way or this way. And then you can move this around, right? Okay, so this is linear. Let's look at quadratic today. Quadratic. All right, let's go here. Quadratic function. So what is the standard form for quadratic function? Okay, yes, you're right. F of x is ax minus p squared plus q. And here I can adjust my a. So let's make my a equal to 1. Okay, let's make my a equal to 1. And let's make my p and q to be 0. So I have a basic quadratic function. So when they both equal to 0, my function is y equal to 1x squared, right? Y equal to x squared. So how does that graph look like? Y equal to x squared look like this, okay? So the pink graph is my quadratic. My blue will be my reciprocal of that. Wow, this is how it looks like. Okay, now actually that's not the. Do you remember we said there are 7 cases? Wow, what 7 cases? It sounds so crazy. So let me show you. This is the first cases. This is how it looks like. Okay, how many invariance point? 1, 2, 3, 4. 4 invariance point. First cases. Second cases is this. When there's only 3 invariance point. 1, 2, 3. When this point touch. The third cases is when there is only 2 invariance point, 1, 2, and then here they don't touch. Wow. Okay. The fourth cases is when the graph is completely positive. So this part in the bottom, like where this little negative part is become, has gone. So if I go to 0, see, no more negative, just this. This is the fourth cases when you have still 2 invariance point. The next cases is when you have just 1 invariance point. This is the fifth cases. And then finally, okay, well, the fourth cases is when you have 2 invariance point and there is a vertical asymptote in the middle. Do you see that? Okay. However, the fifth cases is when you don't have the asymptote anymore. You still have 2 invariance point. Sixth cases, you have 1 invariance point, which is here. They just touch at 1. Finally, you have no invariance point. You have the purple graph, which is your quadratic, and then you have the blue graph, which is your reciprocal function. So for quadratic, it could have 7 different cases. It sounds complicated, but hopefully this software help you link everything together. And as you see, they are all related with the same principle. So in math, it's like this. The outside may look complicated, crazy, complex, but the inside underlying principles are the same. So same principle, you just apply the same principle. You can have 7 different cases, but the principles are the same. What principle are we talking about? That is, you're just taking a reciprocal. So all the 0 become asymptote. Since there are 2 zeros here, you have 2 asymptote. And then the 1 and -1 are the invariance points. Since your purple graph cross 1 and -1 4 times, so you have 4 invariance points. And finally, you have a curve around any segments. All right. And then let's say if your graph hit, if my Q function, let's say the lowest point is at 2, right? Let's say here, do you see this point is at 2? You take the reciprocal, become half. Did you see that? It's become half. Every dot on the pink graph, you take the reciprocal, is the blue graph. So 1, 1, -1, -1, you take the reciprocal are the same. That's why they're invariant point. But then anything other than that, let's say 2, 3, 4, 5, 6, 7, 8, 9, 10, when you take the reciprocal, they become really small. So that's why it's here. And anything between 0 and 1, they're really small. When you take the reciprocal, they become really big, which is here. Okay? So you follow those 3 steps, you will get the answer. And all the cases you follow the same step. Here, you follow the same step. 2 asymptote because there are 2 zeros. 3 invariance point because there's only 1 -1. Like this, the vertex is at 0, -1. Okay, you can also move it left and right. It will be the same. See, it will be the same. You can also make it skinnier or fatter, fat. See, it is the same. Okay, if you flip to the other side, it follows the same idea. It just become other cases. If you flip to the other side, it's become like the 6 cases when we do the other way. Okay, so this is all the 7 cases, but I hope you understand and say that yes, I can understand these cases because it's from the same principle. I just follow the same principle, I will get the answer. Okay, so let's put some notes down. Okay, so for today's class notes, I will put part of it down and then I will summarize it today with another handout. Okay, so go to lesson 5 and go to page 480. And then this is our quadratic function, case number 2. Case 1. So quadratic function, all right, x squared minus 4, its vertex is at 0, 4, 0, negative 4 here. All right. So in here, it show all the values of the f of x function. And now you want to draw a new function that you take the reciprocal of all the f of x, all the y value. This is the result. And same thing, the 0 become undefined. So therefore, you have 2 zeros here. They become its vertical asymptotes here and here. Did you see? All right. So the line has the equation x equal to negative 2 and x equal to 2 because this is where the zeros are. And they become your vertical asymptotes. There's always a horizontal here, horizontal asymptotes here. So how many region does all this asymptotes line break the graph into? It breaks into 6 region, right? 1, 2, 3, 4, 5, 6. Out of the 3 region, you have graph. This region have graph, so that your reciprocal graph will exist there. The other 3 region has no graph. The f of x doesn't exist there, so the reciprocal of graph doesn't exist there as well. Now you mark the 1 and negative 1. So second step, 1 and negative 1 here, 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 here. Where's 1 and negative 1? You think of an imaginary line at 1 and another imaginary line at negative 1. So you have 4 invariance points. Finally, you just draw the curve. This bit, if you just focus on this one, looks like a linear. Well, it's not linear, it's a curve, it's a quadratic curve, right? But it looks like a linear graph, and then you draw for that, and then you draw a curve crossing the invariant point and then being bounded by the asymptote. On here, and then same for this side, like this one looks like right here, looks like a straight line, then you draw a curve passing through here and go over there. Okay, the only complicated part is in the middle. Okay, we have 0, negative 4. We need one more point as an anchor. 0, negative 4, right? 0, negative 4, this point. You take the reciprocal, becomes 0, become here, this point. 0, negative 1 over 4. Here we go, 0, negative 1 over 4. So now you have 3 points that you want to connect the graph, and then you have 2 asymptotes as your guide, right? So you draw a curve along the asymptote, cross this invariant point, cross this point, cross this invariant point, and then just come back to here, approaching the other asymptotes. So that will be your answer. So this is how you do it. Okay, you follow the same 3 steps. 0 become asymptote. Okay, the pen is not very good at writing. Number 2, plus or minus 1 is your invariance point. Number 3, you just complete it by drawing the curves. Okay, same principle. So let's try, are there something they want us to write down? Okay, sure, they want to complete some notes here. So the y-intercept for this function is negative 4. So therefore, the new y-intercept will be 1 over f of x is negative 1 over 4. The x-intercept of the original graph is 2 and negative 2. So now they are 0. When you take the reciprocal, 1 over 0 is undefined. So it's become your vertical asymptote at x equal to 2 and x equal to negative 2. When you give an equation of the asymptote, you have to write x equal to something or y equal to something. The horizontal asymptote is always y equal to 0. So you need to write this. Just don't just write a 0. You need to write y equal to 0, which represent a line. And finally, how many invariant points are there? There are 4 invariant points in this graph, all the 1 and negative 1. And then, when the original function is 0, the graph have a vertical asymptotes. When the function approaches infinity, plus or minus infinity, which means when the function go really big or low, the reciprocal will approach the horizontal asymptote, which is at 0.